In the last unit of this course, we're going to take a look at a closer look at the chemistry of some of our nonmetals. Remember, we can always find the nonmetals on the right side of the periodic table. They're pictured here in the green color. We've discussed some of them at great length. Of course, we have the noble gases in group 18 or 8A. Those are very unreactive, inert gases at room temperature. That gave us the basis of the octet rule, in which 8 valence electrons promotes stable stable configuration for atoms. We'll take a closer look today at some of the nonmetals that we've haven't discussed previously. We've discussed carbon at great lengths, and nitrogen and oxygen. We'll take a little bit look at those. Primarily, we're going to focus on silicon and boron, which can also be called metalloids, but they're certainly not metals, and so this is a good place to discuss them. I won't talk too much about sulfur and phosphorus in this video lecture series, but there is information in your textbook which you should read, as well as more information about oxygen and the halogens. Okay, if we take a look at the percent by mass composition of materials in Earth, we find that oxygen is the number one element that can be found in the Earth's crust. Silicon comes in at number 2 by mass. So we're going to talk a little bit more about silicon chemistry. A few metals round up the rest of the list. So let's first start talking about silicon. Now we know that silicon has 4 valence electrons, and therefore would like to form 4 bonds. Just like the element that's right above it in its family, carbon, of course, likes to form 4 bonds. Unlike carbon, though, silicon only creates or forms single bonds with oxygen. And the reason for that is that the overlap of unhybridized p orbitals, or the sigma bond that forms between a silicon and oxygen bond, is too long for the overlapping or the stable overlapping of unhybridized p orbitals between oxygen and silicon. Since they're further away, a stable bond just doesn't form, so primarily silicons form single bonds with oxygen. Okay, so that you can see, if we take a look at an individual unit of an SiO4 tetrahedron structure, we refer to as silicates. Individual units of this tetrahedron would have an overall -4 charge because of the -1 charges on all of the oxygens if we calculate the formal charge for those. So an individual unit of SiO4 silicate would be a -4 charge. Okay, it turns out that we rarely see, or would not see, individual tetrahedrons of silicates. They either form covalent network structures that we previously discussed briefly, and this would be an example of quartz, both macroscopic and microscopic visions of this. It can form covalent network, actually I should say network covalent bonds. And this causes the melting point of these structures to be very high. If you want to go to the liquid phase, you have to break multiple bonds, covalent bonds, for this to liquefy. Okay, so these structures have very high melting points. Okay, and additionally, if they do not form entirely covalent network bonds, they can form substructures with formula units that have of course, negative charges. Here's the Si2O7, has a charge of -6, this unit structure for a silicate. Of course, when these compounds make, or when these formula units of silicates make compounds, they are going to form bonds with cations. Okay, and the various cations and their ratios forms different silicates or different quartzes, different compounds. You often see zinc compounds, calcium compounds, magnesium compounds in various proportions with these silicate formula units. Here's another silicate formula unit for a tetrahedron that is bound to 3 other tetrahedrons. This creates a system where you have Si4O11 minus 6 polyatomic ion, and again this would bond with other cations to form different quartz structures, different minerals. Okay, just like silicon, carbon also bonds to 4 structures, but as we've seen, carbon can bond to 4 single bonds, such as methane. It can also bond singly or doubly to oxygen. So it turns out that the chemistry of carbon can take a much different approach than silicon, even though it is in the same family, because of the fact that it can form double bonds with oxygen. So carbon does not form covalent networks with other elements. When it's bonded to just itself, we can think of it as making covalent network bonds, and that would be in the case of some of the structures that we're going to talk about next. And that, of course, is graphite, and diamond. Now these are allotropes of carbon. And so these are the 2 different forms of carbon that can be found in nature. Okay, and that's the sort of definition of an allotrope, is that if some those elements that can be found in different various forms of or geometrical arrangements, they are known as allotropes. Here you can see that graphite comes in sort of almost planar sheets, which quite aren't as organized as other forms of carbon, but a different geometric arrangement of carbon forms a diamond structure, and both of these we're very familiar with. Additionally, carbon atoms can be come in different various forms that have a lot of different chemistries. Here is an example of the Buckminster fullerene, a carbon molecule in which 60 carbon atoms are bonded in sp2 hybridization form to make this spherical structure. This compound was awarded a Nobel Prize in 1996 and has spawned some sort of architectural homages to it in various forms. Another form of carbon that won a Nobel Prize more recently, that is graphene. And this is where those sp2 hybridizations of carbon are on a single atom sheets. And it turns out that graphene, because of its this single sheet of this honeycomb sp2 structure, has some really interesting chemistry, and this was awarded the Nobel Prize in 2010. Additionally, you can sort of roll up those sheets of sp2 hybridized carbons that are all linked up in that hexagonal structure into what are called nanotubes. Because of the order of the diameters and often lengths of these tubes are on the nanometer range. You can arrange these in single-walled nanotubes, because, meaning that there's only one layer of these carbon atoms, or you can sort of roll up multiple carbon nanotubes to smaller inner diameters and insert them into each other, or actually grow them progressively into what are called multi-walled nanotubes. And nanotechnology, of course, is making a lot of technological advances in recent times, and the chemistry of these structures is quite interesting and has a lot of very exciting applications. Additionally, carbon can form an ion in structures known as the carbide. So C2 minus 2 carbide can be formed with various metals. Here's an example of calcium carbide. Another example would be tungsten carbide. The C2 minus 2 structure of the carbon forms ionic compound lattices with these metals to form various structures. And these, of course, have vastly different chemistry than your organic chemistry, organic carbons, or even your graphite, graphene, and nanotube chemistry. We'll take a brief look at boron. We've seen boron previously, and it is one of the rare elements that is stable with an incomplete octet, 6 valence electrons, giving it a trigonal planar geometry. Because it can accept electrons, lone pairs of electrons from other molecules, it is known as a Lewis acid, something that you'll discuss in general chemistry too. So there's a lot of different chemistry that boron can do that other elements can't. Naturally, boron can come in up to 5 allotropes. And they're all based on this icosahedron unit cell pictured here, where actually boron is going to form 5 bonds with other borons. And lastly, we'll talk a little bit about the halogens. We can see that most of them, or some of them, are gases at room temperature, fluorine and chlorine. Bromine is actually a liquid at room temperature. And iodine is a solid at room temperature with a melting point of 114 degrees Celsius. We know that they increase in radius as we go down the family, and as we increase their electronegativity as we go up. Some of the chemistry of these, the fluorine and chlorine gases are very toxic. And as we know, all of them, if we abbreviate halogens as X, all of them form strong acids where they will either produce a hydrogen cation in solution and the anion in solution. All are strong acids.